And good afternoon, YouTube. In this video I'll take a peek inside this Tripp-Lite APS1012SW inverter charger and see how it works. As mentioned in the previous video, this is a low frequency sine wave inverter. It operates at the power line frequency and also directly off the battery voltage. This differs from inverters that take the battery voltage and boost it up to a higher level at a higher frequency. Higher frequency and higher voltage both are key to increasing the efficiency in the inverter. With higher frequency, transformers can be smaller, and with higher voltage, the output switching components handle less current. With that in mind, let's take a look at this unit. So this is the AC end of the unit. There are two AC breakers here. One is for the output and the other one is for the charger input. And I've found I can add a switch in line with the charger breaker to turn off the charger if needed. Although that switch needs to be closed for normal inverter operations. Below are two hardwired connections for the output and the charger input. Looking inside, one finds the transformer. It's the bulk of the 36-pound weight right there. And then there's a fan right here between the two halves of the unit to pull air through for cooling. It blows out over the transformer. So here's the other half. You have the fan over here, and then on the other side you've got the MOSFETs and the control circuitry up above. MOSFETs are arranged in 4 banks of 5 parallel devices, so there's 10 on this one big heatsink here that has the 12 volt feeding it through this 200 amp A&L fuse. So there's actually an internal fuse. Here's the two split heat sinks. There's 5 MOSFETs here and 5 down there. This is the red wires that come off the transformer and the black wires. The positive from the battery is attached over to this heat sink. So the heat sinks in this unit are live. If you look at the 200 amp fuse down here and 5 MOSFETs in parallel, that's about 40 amps per MOSFET. So if we go up here, let's look in this upper left-hand corner. So I think this is some noise filtering and protection devices. There's some filters and it looks like some MOVs for output protection. This is all the 120 volt wiring here. All the brown and blue wires come from either the charger input or the inverter output. So the black and red wire here is the output from the transformer, and then the brown and blue wires are either the inverter output or the charger input. And then down here there's the two relays that form the transfer switch, and they might be solid state relays. I can't really get a good look at the part number, but in order to get them to switch in less than 16 milliseconds, they're probably solid state. And you can see right here there's a little isolation slot and probably an opto isolator. It's a 4-pin device, and that's probably what senses the loss of AC power on the charger input and causes the system to transfer over to DC power. So that transfer happens in these two relays. One of them will take the charger power and send it out. The other one will take the inverter power and send it out to the outputs. There's a small inductor here that's probably part of a DC buck converter to supply 5 volts to the control logic. You got your buzzer here, and with all these heavy gauge AC wires soldered on top, I've really never attempted to remove this circuit board to look on the bottom side, but I'm guessing there's probably some surface mount control components on the bottom side, because I don't see anything that looks like a microcontroller on here. There's a little crystal and looks like probably some driver ICs. But if you look at that, there's really not much there considering all this does. It's an inverter, it's a 40 amp battery charger, and it's a 15 amp transfer switch. And that's all done right here. So how does it actually work?